In today's note, we're going to be looking at the different types of cause and effect relationships that can be found between two variables. So showing that two variables are related is quite straightforward when you look at correlation coefficients and coefficients of variation. However, establishing that a change in one variable causes a change in another is more difficult. So these are looking at cause and effect relationships. So there are different types. So first off, a standard cause and effect relationship. A change in X produces a change in Y, or a change in the independent variable changes or produces a change in the dependent variable. So some examples of this may be something like hours studying or hours sleeping or hours stress relieving versus exam score. So if you look at any of these three variables, hours spent studying, hours spent sleeping, hours spent stress relieving, I'm going to compare it to the exam score, we should see that as we change one, it produces a change in the other. You could also look at something, say for example, increasing drop height versus impact velocity. So the higher I drop something, the greater the velocity on impact should be. Right? So that there's a change in X produces a change in Y. Often we mistake or we assume a cause and effect relation just because there's a correlation. So just because we have a strong R and R squared value, we assume there's a cause and effect relationship. However, there are various types and various degrees of a cause and effect relationship. So first one, a common cause relationship is when there is an external variable that causes two variables to change in the same way. So say for example, something like the price of lettuce and tomatoes drastically rise. So if I were to look at these two variables, the price of lettuce and the price of tomatoes, we could see that as one increases, the other increases, but that doesn't necessarily mean that the price of lettuce is causing the price of tomatoes to increase. There could be an external variable that affects both of them in the same way. So for example, it's more likely something else influences this. Or something else influenced the price to rise. So say for example, it could be weather, say maybe amount of rain. Right? If there's not a high amount of rain, then it could cause the price of lettuce and tomatoes and other produce to rise drastically because it costs more. A reverse cause and effect relationship. So this occurs when the dependent and independent variables are reversed in the process of establishing causality. So what this is saying is when you set out to determine a correlation or a relationship or a cause and effect relationship, you would set up your independent and dependent variables. However, through the process of actually determining the correlation, you may find that your independent and dependent are actually reversed. So it's actually what you classified as dependent is actually the independent. So say for example, if you are, say, testing amount of coffee consumed versus levels of anxiety in students. So maybe that's what you're trying to determine with the amount of coffee consumed causes high levels of anxiety in students. However, it may be more likely that levels of anxiety causes more coffee to be consumed. So again, it could just be when you actually go through and determine the correlation, it's actually that the one affects the other, opposite of what you were actually looking at. An accidental relationship, correlation exists, but there is no cause. So there is a correlation between the two, but there is no cause or effect between them. So say, for example, car sales goes down, video game sales go up. So there may be a correlation here. However, there's no cause and effect. It's just an accidental relationship just because, so again, just because there's a correlation does not actually mean that there's an actual cause and effect between the two. A presumed relationship, two variables seem to be related, yet it is difficult to establish a cause and effect or a common cause. So for example, brain tumor rates versus cell phone use. So the two variables seem to be related. However, it's difficult to determine cause and effect between them because there may be too many other variables in play, or it's hard to pinpoint what it exactly causes or which part it actually causes. So strategies for establishing cause and effect. A new drug is administered to a sample of people, and the effectiveness of the drug could be affected by many variables: the patient's age, sex, other medication they're on, diet, exercise, etc. These are called extraneous variables, and this can invalidate conclusions based on correlational evidence. So if we find a correlation between two variables or between the effectiveness of the drug and the people, these could be invalidated because there are so many other variables or extraneous variables that are having an effect or may be causing the actual cause and effect relationship. So researchers, what they might do, they might test the drug on two sets of people with similar characteristics. One, the experimental group, which would receive the drug, and one, the control group, which would receive a placebo or a drug that does nothing. And the comparison with a control group can help remove the effect of extraneous variables in the study. Any differences between the group can now be attributed to the drug. So the key thing here is you're removing the effect of these outside variables by using two sets of people with similar characteristics, having an experimental group and a control group. Another thing that researchers may do is they may do what is called a double-blind study. So it's still taking into the same idea of having two sets of people with similar characteristics. So you're trying to remove those extraneous variables such as the sex, the the other medications, the age, and whatnot. However, what you're doing now is rather than have a single group that's controlled and a single group that's experimental, neither the patient nor the doctor knows if the patient is receiving the drug or a placebo. So that means both the patients or both the participants of the study and the doctors doing it have no idea who received what. It's all random. And in this way, this testing method guards against bias in data collection. It reduces any chance of the doctor or the person running the survey or study to inadvertently influence the patient. Right? If you know someone is on the control group, you may influence them to answer certain ways, or if they're experimental, in the experimental group, you may, again, try to influence their answers. It might be unintentional or it may be intentional. But with the double-blind study, you remove that kind of bias because you don't know who's on the actual drug or not. So again, just some different techniques that you can use to kind of narrow down a cause and effect relationship. So an example, the scatter plot and line of best fit showed the relationship between the number of successful free throws made out of 10 attempts and the number of hours spent practicing for members of a basketball team. So characterize this correlation with regard to cause and effect. So we have, given in our graph, we have our R squared value, which is equal to 0.78. So we could say that with this correlation, 78% is due to the number of hours being spent practicing, and the 22% remaining is left to random variables or randomness. If we go through and we want to calculate our R value, so we can work backwards, because the R value would just be the square root of 0.78. Again, R value of 0.88. In this case, we're going to say it's positive because it's going in the positive direction. We could say that it is very strong. Again, it's close to 1. And we could say that it is a positive correlation. Because again, we can tell based on the direction of the line of best fit. And if we were to look at this, we could then say, as hours spent practicing increases number of successful free throws also increases. So that's looking at the correlation and in terms of cause and effect as well. If we want to interpret the line of best fit, again, to interpret it, we could say it's positive. We could say it's a strong correlation. We could also actually determine what the actual value or what the actual equation is. So again, because it's a linear or a line of best fit, it's y equals mx plus b. Our b value, we can tell, is 0 based on the graph. The y-intercept is 0. So again, this is going back to grade 9 and 10. We can find our slope by doing y2 minus y1 over x2 minus x1, or rise over run on the actual line. And what we can find is that our line of best fit is equal to the linear regression or linear function of y equals 1.2x. So any limitations of this linear model, so some things you may come up with, there may be other factors that affect it. Such as maybe there's injuries to some of the players who are studied. a skill level. Right? Maybe you have just someone who's in a gym class, or you have someone who has played basketball at a high level for a long period of time. So there are other factors out there. You could think of it actually being a small sample size. To accurately say that one thing causes another. And again, there could be other limitations as well. So the key thing from this note is just being able to identify, or at least think about, the different type of cause and effect relationships that you could come up with, and it's not just as simple as X causes Y.